the last thing we're going to look at is, as I mentioned before, most solutions do not behave ideally. And so we want to understand why solutions would deviate from Raoult's law behavior, and how they would deviate, and what those deviations can tell us about what's happening on the molecular level in terms of our two components that are making up our solution. And so if you remember, the assumptions behind Raoult's law involved the molecular interactions, right? What are the forces that are happening among the intermolecular forces for the individual component with itself, but also with other, with the other component of our system. And again, we're only considering two component systems here to keep things simple, but you can extend this sort of analysis to more complex systems where you have multiple, 3 or 4 whatever components. And so we can classify our deviations from Raoult's law, from this ideal solution behavior, into two possibilities. So we can have positive deviations from Raoult's law, and the way to understand whether something's positive or negative is to think about the vapor pressure that's measured versus what you would expect from Raoult's law. So let's look at a plot here to illustrate this. So this is a figure from your textbook looking at a specific mixture that has a positive deviation from Raoult's law. So this is a mixture of carbon disulfide and dimethoxymethane, which shows this positive deviation behavior. So just to make it clear, so the lines down here that are indicated, right, these straight lines, these are the behavior you expect from Raoult's law, where it follows just as a function of the mole fraction, you have this direct relationship between mole fraction and the pure substance vapor pressure, right? Again, x1 p1 star, right? That would be this line here. And the solid lines on the top here and here, these are the actual vapor pressures in the solution. And so the reason we call these positive deviations is that so P actual is greater than P from Raoult's law. Right, greater than the ideal value. Now, why is this happening? Let's think about what this tells us about our interactions between our different molecules. And so for a positive deviation from Raoult's law, let's think about our interactions between 1 and 1, 2 and 2, right? The molecules interacting with itself versus molecules interacting with unlike components, the 1 and 2. In Raoult's law, we assume ideal solution behavior. We assume that all these are about the same. That the everything's about the same favorability. The molecules don't really prefer whether they're around 1 or 2. But with positive deviations, what happens is that molecules interacting with they prefer being with each other, with their same kind. They don't like being around the other kind of molecule. So these interactions are more favorable when compared to the interactions here where they're less favorable. And remember, we're comparing something in solution where they're right up next to each other, it's a condensed phase, versus being in the vapor. Since we're assuming ideal gas behavior, what's happening in the gas phase is that they don't have to talk, they don't have to be around each other at all. They're essentially by themselves. And so what really matters here is what's happening in the solution phase. Now, the fact that things would rather be with themselves, that those interactions are more favorable, right? 1 and 1 and 2 and 2. In this example, carbon disulfide would rather be with other carbon disulfide molecules than with dimethoxymethane, means that whatever's the minority component of the solution would rather just go into the gas phase. It'd rather get away from, in comparison to our theoretical ideal solution behavior. It would rather get away from these 1 and 2 interactions here, which are not as favorable, and so the vapor pressure increases relative to the ideal solution behavior. So that is a positive deviation. That's what it tells us about what's happening in terms of the intermolecular forces. We can have the opposite happen, right? So it is possible to have a negative deviations. And that tells us that the opposite is true. So again, getting a plot that I can show you. Let me grab this and copy it over. So this is less common, the negative deviations are, but still possible. So this is again a figure from the textbook showing Raoult's law behavior. Now the Raoult's law behavior again is the straight lines here on the top. And in this case, our actual vapor pressure, the solid lines on the bottom, is lower than the Raoult's law behavior. And this tells us if we're thinking about our different types of interactions here, the unlike interactions are actually more favorable in comparison to the molecules interacting with their same type of molecule. So we have the opposite effect of what's happening with Raoult's law, with the positive deviations from Raoult's law. So in this example, trichloromethane and acetone have a very strong interaction with each other, which leads to a more favorable, and so they'd rather be in solution. They'd rather be in the condensed phase next to each other than going into the gas phase, in comparison, again, to our example where you have just a pure substance, or you just have the ideal type behavior. And so this gives you negative deviations from Raoult's law. And again, that can tell you something about the intermolecular interactions. We have one more video after this where we're going to talk about one final concept with liquid-liquid solutions, which is the idea of azeotropes.